students, and in this video we are going to discuss about the mean value theorem. Mean value theorem, there are two prominent mean value theorems in the standard 12 right now. However, there are some other mean value theorems also, but we will discussing them in a separate video. Right now we are focusing only on the two mean value theorems which are the part of the standard 12 of the Indian and International Board. One is called as Rolle's theorem. Now, what is a Rolle theorem? Rolle's theorem. Rolle's theorem says that if a function, if fx is a real valued function, defined in such a way, that number one, that fx is continuous on the open interval a b, means the function fx has been defined in such a way that the fx is continuous on closed interval a b, means at a, at b, and within a and b the function should be continuous. Number two, fx is differentiable on open interval ab. Closed interval means the x should be, and this open interval means the values should be, the end points are not included, means the point a and b. So in the closed interval, this a and b are also included. In the open interval, a and b means anything between a and b, but a and b are not included. That's why I'm making this one as a little curve. And the third condition is that if fa equal to fb, so if these three conditions meet, then there exists a number, then there exists a number c between open interval a and b such that f dash c equal to 0. Now, if we try to understand the graphical significance of this statements, then we find that first fx is continuous on a and b. It means there is no break in the graph of the function between a and b. So suppose if I have my function, it goes like this. This is my a and this is my b. It means it should be continuous everywhere. There is no break in the graph of this function. This is my x-axis, this is my fx. First condition. Second condition is that it should be differentiable, that at each and every point within the domain of a and b, their differentiation should exist. Means graphically you should be able to plot a tangent at each and every point between this a and b, right? So means at each and every point, and we are not including the a because here the left hand differentiation is not possible, and here right hand differentiation is not possible because the function is only defined in the domain of a and b. So our function can be like this. And then third condition is that fa is equal to fb. Now this point a, and this is your fa, and this is b comma fb. So this point is your fa, and this point is your fb. These things should be same. Means our graph should not be like that. Our graph should be like that. So that should be our AFA. This is AFA. This point is AFA. This one I'm writing here, and this is VFB. Now you see that if this is the condition, then there is definitely a point C between A and B where the f dash C means the dy by dx is 0, means the slope of the function at that point will be will be parallel to x-axis. Means because from here to here it is a decreasing function, from here to here there will always be a sure turning point at C, and this f dash C is 0. So this is the significance. I again elaborate these 3 points, that the fx is continuous on the open interval AB, means there should not be any breakdown in the graph of the function between the point A and the point B. So this is my point B. Second, fx is differentiable on AB, means between each and every point, like between A and B, at each and every point the function's differentiation should be exist, means there should exist a tangent. Differentiation is just a tangent. So there should be at each and every point a tangent is possible, means here a tangent is possible, here a tangent is possible at each and every point. Now if you just try to understand by visual inspection, then the tangent at this one point will be like this, at this one it is like this, at this point it is like this, here it is like that, and here it is like that. It means there are different type of tangents, differently directed actually. So it is just like, but these 3 conditions saying that there is differentiable, means there is a possibility of finding out the tangent at each and every point within these 2 points A and B. And third, FA is equal to FB, means this top point like A, FA and the BFB, means this point should be same. Another condition also is possible, like suppose if we have another path, it goes like this. So again it is continuous, it is differentiable, and at each and every point the differentiation is there. And then also you see there is a possible point by visual inspection also you can say that f dash C will be 0. Or even if it is like that, then there is a possibility that you can have some point between these 2 points A and B where the tangent is parallel to x-axis, that is tangent is equal to 0. So f dash C, you can always find a point function, because this graph is suggesting that the graph is somewhere, and one more possible case is there, if it is a straight line instead of just it is a straight line, then also you see that this line itself is parallel to x-axis, means there is always a point C where the graph will be, the tangent will be parallel to x-axis and f dash C will be 0. This is the significance of the Rolle's theorem. Now we'll take some example to understand what does it mean actually. Now I have taken one example, and the equation example says that show that function fx x minus a to the power m and x minus b to the power n, mn belonging to natural number, is defined on the open interval, and the Rolle's theorem is verified, but open interval is AB. So now you see what is fx, it is a polynomial function, and we know that the polynomial functions are continuous everywhere. So write down first line, since fx is a polynomial function, of degree, this is not required, you don't need to write a degree, but I am just writing because this is x to the power m and this is x to the power m, these are multiplying, so the order or degree will be m plus n. So fx is a polynomial function of degree m plus n, so it is continuous. So the condition 1 meets, so it is continuous on AB, first condition. Now polynomial functions are also derivable at each and every point. So the same reason fx is derivable. If it is derivable, what will be the differentiation? So you can also find out f dash x. Now I'll use UV rule, so it is m x minus a to the power m minus 1 x minus b to the power n plus x minus a to the power m n x minus b to the power n. So if you take x minus a n minus 1 and x minus b n minus 1, this is n minus 1, common, then you will get m x minus b plus n x minus a. Okay, so you see that its differentiation existing, and this one gives you the form of mx plus nx minus mb minus nma mb na, and this is x minus a to the power m minus 1 and x minus b to the power n minus 1. They haven't asked you to prove that, but I am showing that yes, you can see its differentiation is existing. If you put the value of x as a here, but we don't need to find differentiation at a because this should be the open interval. So you can take any number between a and b and you will find this is a possible value. Now, third condition is that fa should be equal to fb. fa should be equal to fb. So when you put fa here, so this part vanishes because x minus a, so a minus a will become 0. Similarly, b minus b will also be 0. So all these three conditions are meeting true. Now there should exist a value c. Then the rule says that there should exist a value c such that f dash c is 0. So we have already found f dash c. Now we have to see what is f dash c 0 gives. So f dash c will be c minus a. Here in this very same expression I am writing x as c. So c minus a whole to the power m minus 1, and then c minus b whole to the power n minus 1, and this is mc plus nc, mc plus nc minus mb minus na. Okay, so now this one has to be 0. So if you set it to 0, it means this part is 0. So therefore what do you conclude? That mc plus nc equals mb plus na. So now you take your c common. This is m plus n, mb plus na. Now c equal to mb plus na upon m plus n. It means we have only to verify whether the c lies between a and b. Now those who have remembered the significance of this vector internal section or the internal section of a point, then you see that if a is a coordinate here and b is a coordinate here, and if c is a point which divides a and b internally in the ratio m is to n, then the c's coordinate can be found as mb plus na over m plus n. I mean, this one satisfies that the c lies in this interval a and b, and hence the Rolle theorem is verified or proved. Thank you very much, and in the next video or in the next part I will talk about the Lagrange's mean value theorem.